Section 9.4, we're going to look at comparing sets. And in particular, we're going to have two different tests that we can use for comparison of sets. Both of them have nice things about them, and both of them have drawbacks. They can be used interchangeably, typically speaking, but sometimes there's maybe a more obvious choice than the other one, right? So our first one we're going to look at is called the direct comparison test. So the condition that has to be satisfied on the direct comparison test at the beginning is what makes this difficult to use sometimes. A sub n has to be less than B sub n, okay? So you cannot have sequences that are close together but maybe like oscillate around each other. They have to both, they have to have a constant relationship where one's smaller than the other one. Not only that, but the relationship has to be such that if the smaller one is the one that's going, if one of them is going to diverge, it has to be the smaller of the two in order for you to know something about the other one. And if one of them is going to converge, it has to be the bigger of the two, or you don't know anything about the other one. So it doesn't always work out that way. You can imagine if you had two sequences, if you had two series that were pretty much doing the same thing, but they didn't strictly follow this less than relationship, the expectation would still be that this kind of a pattern would hold, right? Like it shouldn't matter if they're close enough, quote unquote, then it should still be okay. Well, if that's the case, this is not the test for you, at least not the test for that particular example. Okay, but when it works and you can establish the relationship of the less than situation and what's converging or diverging is very clearly the smaller or the larger as it needs to be, then it works really well and using it is really easy. Okay, so we're going to do an example.
What is the upside down A again?
It means for all.
Okay.
Yeah, for all. An A like for all. Yes. Anything else? All those symbols. I avoid using them usually in Calc 1 because I don't want to confuse people. So if you're like, shouldn't use them in Calc 1, that's probably you took my class. I'm sorry about that. All right. So we're going to do an example with direct comparison. Okay. So we have a sequence, a series. The sequence inside is n squared plus 1 over n cubed minus 3n minus 2. And more or less, the parts of this expression that matter are the power parts at the beginning, right? I mean, they dominate what's happening. So really what we have here is n squared over n cubed. That's really what's going on in the long-term scheme of things, right? And if you were to simplify n squared over n cubed, what would you get? 1 over n. Yeah, 1 over n. Okay, so we're going to write out like a sequence of steps that shows that 1 over n really is going to work for what we need it to work for. But it's a really good idea to get in the habit of sort of intuitively deciding, what do I really have here? That's the gist of what I have here before we start working with the technicalities of the less than equal to parts, okay? All right, so we're going to take a look at the n squared plus 1 over n cubed minus 3n minus 2. And we're going to eliminate pieces of this as we go, because we essentially want to eliminate everything over here. Didn't get that right. Everything over here wants to go away. We want to show that we can get rid of it and we still have basically the same thing, okay? So what we're going to do is we're first going to eliminate, it doesn't matter what order we do it in, I'm going to eliminate the 1 in the numerator. So I'm going to change this to n squared, and it's over n cubed minus 3n minus 2. Now, this is a true relationship. What I just changed it to is smaller than what I started with. Why? Because I subtracted 1 from the numerator anyway, right? I removed a little bit of it, so it became smaller. Next thing I'm going to do is I'm going to remove the 2 pieces from the denominator that I wish weren't there. Now, it's definitely created something that's smaller. Why? I'm dividing by more. Yeah, so when I took away the minus 3n and the minus 2, those 2 pieces, I actually made the denominator bigger. And a bigger denominator makes the fraction smaller. Okay? The denominator part always is the trickier one to sort of think through slowly. Yes?
So if that had been a plus 2 instead of a minus 2 on one, we couldn't have just gotten rid of it.
Right. And then in those cases is probably the cases when we're not going to use this test. Yeah, so you can see, like, it has to be really specific, right? I can't go removing subtraction from the numerator, and I can't go removing addition from the denominator and make this work. It has to have a very defined form for this to be a thing that happens. At this point, however, I do get 1 over n, which is what I'm wanting to do. So the two pieces that I'm trying to compare now are where I began. So this piece right here with this piece right here. So this piece that I started with is bigger than where I ended. So this is my b sub n. Okay, the way that this was set up, right? The b sub n was the larger of the two. So this is my b sub n, and this one's my a sub n. And it looks like this. It actually is strictly greater than, but if you want to put greater than or equal to, it's not going to hurt anything. It fits the pattern as long as what happens next falls into the right category. So this sequence, when I put it into the series notation, does something specific. Do you know what happens to, oh wait, what am I doing? Off on the wrong screen. I'm doing calculus 1 now. N equals, we have 2, right? 2 to infinity. Oh my goodness, I'm sorry. Okay, n equals 2 to infinity. What's this going to do? Converge or diverge?
Does it converge at 0?
Okay, so we've got differing opinions sitting right next to each other. So why do you think it converges, Zach?
Well, if it goes to infinity, because we have 1 over n.
Yes.
I was just thinking if you plug infinity in, it's going to go to 0.
Okay, so I agree with you that the sequence goes to 0. Maggie?
It diverges if you do the p-series test, 1 over n to the 1.
Yeah.
1 is, p is equal to 1.
Have we talked about the harmonic series?
Yes.
We did that, right? Okay, I thought we had. So this is the harmonic series, which we can think of by the p-series test, we can think of by the integral test, or we can simply justify it as the harmonic test. This is the one that sort of destroys the idea that just the sequence going to 0 is enough. So the sequence does go to 0, but the series is infinite here. The series has no limit. So this actually diverges I'll use the one that Maggie said, so this is by p-series. You could do by the harmonic series, or you could also do by the integral test.
So if p is 1, it still diverges.
Yes,
It has to be greater than 1.
correct. It needs to be greater than 1, strictly greater than 1 for the p-series to actually say that it converges. Exactly. Okay, so this diverges. So what I just found out is that the smaller one diverges. Okay? The smaller one diverges. I'm in case 2. My a sub n, which is minus 1 over n, diverges. So it's going to mean that the one that's slightly bigger also diverges, which should make sense, right? If I've got something smaller going to infinity, then clearly what I'm working with also will go to infinity. So, let's see. So by the direct comparison test, feel free to write that out. The summation from n equal to infinity of n squared plus 1 over n squared minus n cubed minus 3n minus 2 diverges also. Okay, so now imagine we set this up and the 1 over n was actually bigger than what we were dealing with. Right, we had some addition and subtraction in a different order or something like that, and when we found the most reasonable thing to compare it to, it was actually bigger than what we liked, right? It was bigger. Now, that's not necessarily a bad thing, because if it's bigger and it converges, we can still use it, right? But if this one was the bigger one, and it does in fact diverge, then this test doesn't work for us. Are you with me? Okay, so imagine what's really going on from a visual perspective. Actually, this screen's got more space on it. We have some sort of a sequence, and I'll draw it in a function notation, or like a function, like a graph, so that it looks continuous even though our sequences are not. So we have this sequence that has this corresponding function. And if this diverges, and we have something slightly above it, it would make sense that it diverges as well. It's bigger. The thing that's underneath it is getting too big, so this one's clearly going to get too big. Likewise, imagine that you had, actually I put that back, you had this piece, let's say this is 1 over n squared. 1 over n squared, the summation of it actually will converge. And you're sandwiched in such a way that your value is actually beneath it. Well, if 1 over n squared was your, like limiting function on top, and it's going to converge to some number, and we're smaller than that, it's going to converge as well. Now, it doesn't say what it's converging to, once again, but just that it does. Okay, we've got one more example with direct comparison here. Oh, I lied. We don't. We have a limit comparison test. I was working on notes from another section where I had 2 examples in each thing. So sorry. All right, limit comparison test. Now, the limit comparison test looks at what we just did and said, well, that's silly. If the function is really 1 over n, then it's going to behave the same way 1 over n behaves. It really doesn't matter if it's slightly bigger or slightly smaller. If it's really close, it should do the same thing, right? And if the function's 1 over n squared and it's slightly bigger instead of being slightly smaller, it should still do roughly the same thing that 1 over n squared does. So this sort of hand waving is saying that it should do it sort of the same way, and if it's close enough, is exactly what the limit comparison test shores up. So we have positive sequence, okay? And what we do is we take the same sequence, like the a sub n, the b sub n, just like we did before, but we find the limit of them instead, okay? The limit of their ratio. So we have the limit of a sub n over b sub n, and it actually equals L, where L is finite and positive. Okay, so it can't actually be a 0. Then they either both converge or they both diverge. So the benefit in this theorem is that I don't have to worry about whether it's bigger or smaller. I don't have to do any of this less than, or greater than statements. None of that's relevant. It doesn't matter. But the trade-off is that I have to find the limit of the ratio. Okay, there's a trade-off. We don't get anything for free. But in some sense, it makes sense that they would both do the same things, right? They should. If they're close enough, and the close enough is that the limit has a constant ratio. That's what it means to be close enough. That the ratio of the limits, the limit of the ratios, is a constant, right? And it's greater than 0. So let's do one then, so you can see how it works. So Noah, do you see that addition on top? And we have addition on bottom this time, right? That's going to cause a problem. If I'm looking at this, the numerator, as I take pieces away, is going to be getting smaller, but the denominator, as I take pieces away, is also getting smaller. And if I have both pieces getting smaller, it's hard to know exactly which one's going to be dominating what's happening, right? So I'm not going to be able to actually worry too much, or I'm not going to be able to say for certain if it's bigger or smaller using any sort of simple process, right? It's not going to be easy to determine, which makes the direct comparison test for this one not very easy to work with. So what we're actually going to do is we're going to say what this is approximately equal to instead. So if I have n cubed plus 2n plus 3 over n to the 5th plus 2n plus 4, what is this approximately equal to without reducing the exponents and so forth yet? What are we really looking at here?
1 over n squared.
Yeah, so you're looking at the 2 pieces at the beginning. So the n cubed over n to the 5th, the dominating pieces at the beginning. And if we reduce it, just like you'd said, you'd have 1 over n squared. That's basically what we're working with here. Does that make sense? What does 1 over n squared do as a summation? Converge or diverge?
Converge.
It converges. How do you know?
P series.
Yeah, it's p-series because the p-value is 2 in this one, right? This is going to converge. So my expectation is that what I began with will also converge. But there's something I have to show before I can actually use the limit comparison test. I have to show the limit of the ratios, okay? So it doesn't really matter which one of these you put on top. We're going to do the limit as n goes to infinity. I'll just use the first one I had, so n cubed plus 2n plus 3 over n to the fifth plus 2n plus 4. And then it's a ratio between that and 1 over n squared. Before we go any further, I'll flip my fractions. But that's the ratio that we're looking for here. And I'm trying to remember if I have. No, it's fine. Okay. So we're going to have the limit as n goes to infinity of, that's not going to give me everything, n cubed plus 2n plus 3 over n to the fifth plus 2n plus 4 times n squared, or n squared over 1. So we'll increase our powers throughout the numerator by the number 2. So I have n cubed becoming n to the fifth, the 2n becoming 2n to the fourth. I'm off my screen. Let me shift this all over just a little bit. 2n to the fourth, and then the 3 becoming 3n squared. Here we go. And then this is...
Should the end of the fourth be end of the third?
Yes, thank you. Too much zooming in and zooming out. Appreciate it. End of the fifth plus 2n plus 4. Okay, so far so good? Okay, this is limits like we were doing back when we had section 9.1, right? Now you're seeing why we did 9.1, right? It comes into play a lot. So we're going to have the same thing we have here. I'm going to move this down a line. And we're going to multiply by 1 over n to the fifth. So we have 1 plus 2 over n squared plus 3 over n cubed over 1 plus 2 over n to the fourth plus 4 over n to the fifth. And a lot of these go to 0, right? Yep. All 4 at the end go to zeros. What's my limit? 1. And in particular, 1's bigger than 0. I know it feels silly to write it down, but it is. It's a true statement. It's part of what we had to prove. This 1 is greater than 0. Right? So what does that tell me now? Well, it tells me that I've got the limit that it's satisfied in the hypothesis is satisfied. I have two functions, a sub n and b sub n, and their limit ratio, the limit of their ratios, is a constant that's bigger than, or is a number anyway, that's bigger than 0, right? So then that means that either both of these converge or both of them diverge, and we've already established what they do because, let me get another screen here. We'll go with a chalkboard. The limit as n goes to infinity of 1 over n to the n squared converges. And what was the reason why?
P-series test.
Yeah, it converges by p-series. Okay, so I have to state why I know each of them works. This one converges by p-series. So why will, that shouldn't say limit at the beginning. I apologize, it should say sum from n equal 1 to infinity. I've been doing limits in Calc 1 this morning. This is why my limits keep coming up when they're not supposed to. So my summation, did these start at 1 or did they start at 2? 6. Let's start with a 6 then. N equals 6 to infinity. Of n squared cubed plus 2n plus 3 over the n to the fifth plus 2n plus 4. What will it do?
Converge.
And why?
Because no one has comparison test.
Converges by the limit comparison test, which I'll abbreviate. Feel free to do so if you wish. So either way, you've got something to prove in the hypothesis that's the majority of the problem. The majority of your problem is actually doing the hypothesis part for these two tests, right? On this one, it's showing that this limit has this certain feature, that it ends up being a finite value that's bigger than 1. And on this one, It has to be that you've got actually the right ratio. Is it bigger always? Is it smaller always? How do you justify that it really works? And you can't justify this by saying, I'm going to go from here to here, and I looked at my calculator and it's always above it. That's not justification, right? This is not what we're talking about. That's why it's so important that we have this other test for those cases where it's really messy to actually try and show it for real, right? If I really have to go through and justify that this is really bigger or really smaller, that's not an easy task to do for this problem. And therefore, using the limit comparison test on this one made more sense. Now, could we use the limit comparison test on this? Sure you could. Absolutely. You wouldn't have to just justify whether it's bigger or smaller, but then you'd have to do your limit of your ratios, and that may or may not be more work than what you wanted to too. So it's not necessarily that you have to do it by the direct comparison test here. It's just the direct comparison test happens to work, and that's what we were working with in this particular problem. Any questions at the moment? Okay.